This is Geographic Data, an introductory tale. Welcome to the talk. This is a pre-recorded talk, as you know, so I'll be around, hopefully, to answer your questions in the chat. So I'm going to talk a bit about how to work with geographic data. The reason for that is that maps are cool and they're fun, and it's really a useful skill. Many people get a bit dissuaded about it because it's a bit of a jungle out there with all the formats and tools and the different programs, and it's a bit frightening. So I'm going to show you a bit how to start working with that. I won't show you everything, obviously, because it is a jungle out there, but just to give you an example of how to work with a bit with data and what you can do with it. So before we start, a bit about me. I'm Adam. I'm been in the field of open data and data in general for over 10 years. I'm one of the founders of the Public Knowledge Workshop, Hasadna. I'm currently working as a consultant and as a software developer in Wildtrue Industries. Okay, so let's start. And the way we're going to do it is I prepared a notebook, which you can also see in my GitHub page. I'll share the link in the talk description. And the idea is that we have a few scenarios of what we want to do, and we'll just follow the code and see how we accomplish that. So first scenario is pretty simple. Let's say we're in a specific location. We want to find the nearest river in Israel to our current location. So that's the first scenario, and let's see how we do that. So first of all, we need to find where is Israel in general, where its coordinates. And for that, we're going to use something called the Gadm Database. So Gadm is a database that basically contains all the administrative regions in the world. So every district or region that is somehow defined in the world is there. And we're going to use a library called Fiona to open that database and try to find Israel in there. So I have a link here, which is where you can download it, and you can see I already downloaded it. It's 2 gigabytes in size. You can obviously download a subset of it just for Israel, but we're not going to do that. So what I'm doing here. So I'm opening with Fiona this package. It's called the Geopackage. It's one of the formats, one of the many formats that you have for geographic data. And I'm iterating over all the items. Each item has a properties attribute, and I'm going to find all the items that their name 0, sort of the highest level administrative region, is Israel. And now I'm just printing the type and the name of what I found. So when I run this, I get just a list of all the districts in Israel: Golan, Adarom, Haifa, etc., etc. Each of those is basically given as a GeoJSON feature. GeoJSON is one of the most important formats that you'll need to know. If you need to learn one geographic format, that would be it. Each feature in GeoJSON is basically an object which has 2 properties. One is the properties property, which is contains all the different properties or attributes of that specific feature, and a geometry. Geometry basically defines how this feature looks like. It could be a point, a line, a polygon. So let's see, for example, the last region here is Tel Aviv. So let's look at it. And let's look at its geometry. So it's basically, this type is multi-polygon. It means it has multiple polygons which are not connected to one another. And you can see the coordinates. So these are the coordinates, very similar to GPS coordinates, and you can see all the coordinates, and it's a very long list because it's a very detailed polygon of the boundaries of the Tel Aviv region. But it doesn't say a lot to us because it's just a long list of numbers. if we want to view GeoJSON, we have two options. So we have, first of all, the GeoJSON website. We can copy paste the GeoJSON into it or use the GeoJSON.io package in Python. And this is how it looks like. So basically you just call display with the data, and what you see is basically this. So you have here on the right side, it's a GeoJSON. On the left side, you see how it looks like, and you can see that the coastline is very detailed, and you have the municipal borders. It's not entirely accurate sometimes. Sometimes it differs a bit from the actual borders, but most of the time it's pretty correct. Okay, but we want to get a geometry of all of Israel because we want to find the rivers that are in Israel. So now we're going to use a package which is super powerful. It does all kinds of 2D shape manipulations called Shapely. And to unite multiple geometries, we basically call a function called unary union. We convert the geometries to a Shapely shape using the function shape. And so this is basically combining all those shapes into one big shape. And next thing we want to do is simplify it, because as you saw, it's very detailed, and when creating a border of all of Israel, it's going to be very, very big, very big data with lots of different points. So we want to simplify it a bit, so it doesn't look so big or too many data points. And this is how it looks like. So this is Israel. It's not that big. Eventually, we got a coordinate which is just basically one polygon. And again, we can use GeoJSON.io to show how it looks like. So we call the function that we defined earlier, and we get this this polygon, which is basically a simplified version of the combination of all the different districts. And we can also use IPython. If we just type in shape of Israel, then we get that very little representation of that polygon. Okay. Next up, we got the borders of Israel. So now we want to find all the rivers that are in Israel. So to find that, we use a database which you already probably know, which is called Openstreetmap. It's an awesome tool, and all the data is free and available. So let's take a look at for example, at the Hayarkon River. So we use OpenStreet browser to see the properties of different items inside inside OpenStreetMap. So this is, you can see here the exact shape of that river. You can see that it has a line segment and a polygon. So you see the sort of the line that's in sort of defines the path of the river, and also a polygon that actually defines the shape of the actual water body. And on the left side, you can see all the properties of that specific feature. The most important thing here is we have a property that says that this is a river. This is not a sea or a lake or anything else. So we're gonna come back here, but we wonder, okay, so we have something called a river. What do we have other options? So you can also take a look at the OpenStreetMap wiki and see that we have, aside from rivers, we also have something called a stream. So we're gonna try and filter OpenStreetMap by looking at stream and river. So this is the plan. How do we do that? So first of all, we can download all the water data from OpenStreetMap using a site called OSM Data. So this is the site OSM Data, and you can see that we have here filtered version of OpenStreetMap based on the type. So we can download all the buildings, all the natural features, all the places, and here in the end we have all the waterways, which is what we're interested in. It's a pretty big file. It's about 18 gigabytes of data, I think. Let's see. Yeah, this is the file. Luckily, I already downloaded it, so you don't have to wait now. So we're gonna go back here and gonna list the layers inside that file. So we have here the points, the lines, and the polygons. And as you remember, we are interested in the lines, not the shape of the water, but the actual path of the river. So we're gonna open the file with Fiona and choose the specific layer. And now we're gonna iterate on all the rivers, but we don't want to iterate on all the rivers in the world. We're going to iterate on the rivers that are inside a bounding box. What bounding box? We already have the Israel shape, so we're going to take its bounds, and we're just going to iterate on the rivers that are inside these bounds. Then we're going to check, is it a river or a stream based on the properties? Then we're going to make sure that it has a name, because rivers with no name are not interesting for us right now. And we're going to take the geometry of that river. Finally, we're going to check that it actually intersects Israel, because we took the bounding box, but it could be, you know, in the bounding box, sort of in the rectangle that contains Israel, but not inside Israel itself. So we're going to make sure it actually intersects with the geometry of Israel. And if it does, we're going to append it to the Israeli rivers. And after running this, let's see what we get as the first river. So we get a feature which is Nahal Ramon. We can see all the features, all the properties. Some of them are empty. All of them are empty, actually, in this case, except that we can see that it is a stream, it is intermittent, it has an AD, and we can see the geometry, which is a line, basically, with all the points inside. Super exciting. Okay, so now we want to find the nearest river. And let's try and assume that we're currently in this specific location. This is Tzomet Masmia, or Tzomet Reem, specifically. So the first way to do it, and it is the wrong way to do it, let's try and go over the code, and then we'll understand why it's the wrong way to do it. So very simply, we iterate over all the rivers in the Israeli rivers list, and we try to find the distance. So we take the shape of the river, we calculate the distance from my location, and if it's smaller than what we currently find, then we replace the minimal distance and the nearest river. And then we print the distance and the nearest river, and we get some result, but we get a distance which is, I mean, what are the units of that? So why is this the wrong way of doing that? So the reason is that you cannot do distance calculations on coordinates, because as you know, or hopefully you know, Earth is a sphere. It's not flat, and when doing calculations, you need the distance calculations, which is the square root of the difference of x and the difference of y. This only works on a plane. So all the mapping and all the people study that, you know, for years, is how to is obsessed with how to map the sphere onto a plane. If you know, this is a regular map, but you can see that for regions near the equator, it looks pretty normal, but then when you go to the poles, it becomes really warped. And here the x and the y, I mean, they're not on the same scale, so you cannot actually calculate the distance here. There are tons of different kinds of projections. You have the standard and oblique and transverse. Frankly, I don't know half of this stuff. It really doesn't interest me, because again, I'm a software developer, not a cartographer. But what I do know is that when you want to do distance calculations, you need to map all the coordinates to a system that is as a plane as you can have it. And the way you do that is you create a projection, which is basically the way of saying mapping 3D into 2D world. So you create a projection that is based on the point that you're interested in. In our case, it would be that location, our location. And then we map all the other features in the world onto that plane. We do the calculation there, which is pretty accurate because it's very nearby. And then we can map it back again to the world coordinate system. So let's see how it's done. It's a bit frightening at first, but it's really not that complicated. So to do the projections or coordinate transformation, we use a package called PyProj. We define something called a CRS, which is a coordinate reference system. The most important thing to see here is that the base latitude is my location, the base longitude is my location, the x and the y, and we want the units to be in meters. So when we do distance calculations in that system, we'll get results that are in meters and not anything else. And then we create a transformation from CRS Epsg 4326 to our CRS. What is Epsg 4326? That's a good question. So Epsg is basically an index of all coordinate systems. And the number 4326 is basically the name of our regular, well-known system, the one that you see in GPS or in Google Maps. It's also known as WGS84. We can open the catalog and let's see how it looks like. So this is the catalog. It's EPSG.io. We can see all the coordinate systems here. You can see the exact definitions, etc. Super not interesting. But the important thing to know is that it has a number. If you work with Israeli data, it will be sometimes given in a coordinate system called the Israeli New Grid or ITM. It also has a number. It's EPSG 2039, and it's only defined in the area of Israel. And again, if you want to convert data from that specific coordinate system to the regular one or whatever, now you know how to do it. You just need to define the exact EPSG. If you want the CRS for that specific coordinate system, you can go to here and you get exactly the definition of that CRS. So everything is ready for you, so you can just take it and convert coordinates. Okay, so let's go back to the code. So we define the CRS, we define the transformer, which is what transforms coordinates from one another. And we use this transform function from Shapely to use the transformer to transform my location to the new coordinate system. And not surprisingly, my location gets the coordinates 0, 0 because it's the center of the world in our coordinate system. So cool. So now we want to convert all the other rivers to that coordinate system and then calculate the distance. So first of all, before we start, I'm going to do here something which is basically okay, no, we don't need to do that, sorry. We go over all the rivers. We create a transformed river, which is basically transforming the shape of the river using our transformer into our coordinate system. Then we calculate the distance, transform river distance from the origin. And again, we check to see if it's mean distance, and now we can print the minimal distance and the nearest name, and the units are actually meters. So we get 121 meters and 38 centimeters, and we can actually check that is correct, and indeed it's 121 meters on the map as well. So that's pretty cool. What happens if we want to calculate very long distances? Then we use a Geopackage, which actually has a distance method that knows how to calculate distances over a globe. which is an entirely different way of calculating distances. So, for example, we wanted to know the distance from Wall Street to Tzomet Masmia. We know that it's almost 10,000 kilometers. Okay, scenario number 2. Let's say we wanted to calculate which river is near the most population in Israel. So that's a good question. And for that, we will use a different kind of geographic file. The geographic data that we saw until now was vectoric. We saw the different features. It was a line, a polygon, a point. A different kind of geographic data is given as raster data. We can download, for example, this data from WorldPop, which is an estimation of population. And the data is given as a grid of basically 100 meters over 100 meter cells. And you basically get an array of values. Each value has sort of a center coordinate and an estimate of the number of people living in that specific cell. So to open a raster file, we use raster.io. We can open this file. This is Israeli population 2020 constrained. It's given in a TIF file because it's basically an image. The file itself is not that big. It's almost 3 megabytes of data, not a lot. Then we can just plot it using pyplot as an image, and you can see this is the sort of a heat map of the population in Israel, which is pretty awesome, I think. And this file also has a coordinate system. So if we take the file, the pop file, and we see it's CRS, we can see that it's CRS from ESPZ 4326, which by now you know that it's just the regular coordinate system. So we want to calculate the number of people living within a 1 kilometer distance of each river. So what we want to do is take the line of the river and use a method called buffer, which sort of inflates it a bit. So we take the line. First of all, we want to collect all the rivers or all the segments of rivers by the same name. So this is a bit of code that basically takes all the rivers and create a dictionary based on the union of all the segments that have the same name. Pretty straightforward. And then we can take, for example, a sample river, which will be the Yarkon River, and you can see here the sort of the path of that river. And again, we do a coordinate transformation. So we try to find the center point of that river. We create a CRS exactly as we saw earlier. This time we want the units to be kilometers. So it's not meters, it's kilometers. We create a transformer from CRS to our coordinate system and an inverse transformer that will take coordinates back from our coordinate system to the regular one. We transform the sample river. This is what we do here. We take the sample river and transform it to our coordinate system. We can print its length. So we can see that it's 27 kilometers in length. Then we use the buffer method. We add a 1 kilometer buffer over the river and transform it back to the WGS84 or the regular coordinate system. And you can see that we got a small little caterpillar here. So this is the river with a 1 kilometer buffer around it. Next up, we use a mask. So we take the population data and we mask it using that buffered river. We crop it when we tell it everything that is outside of the map, give it a value of 0. And what we get is this basic mask of that caterpillar with the population data. So the river flows somewhere in here, and we can see the population around it. And finally, to calculate the population, we just need to sum on the resulting array. and we get 176,000 people live in 1 kilometer distance of their con, which is, I think, a pretty cool result and a good place to stop. So let me know if you have any questions. I'll be around in the chat if you need me, and have a great day.